I want to start by thanking CTBUH for giving us the opportunity to present Hummingbird, an innovative tuned mass damping system. My name is Hans Utz, and I am the CEO of Hummingbird Kinetics. I'm going to start a little bit with a background on what harmonic damping is itself and why it's necessary, and actually some of that background probably applies to almost all innovation in this space. I'll spend a little bit of time on the history of Hummingbird, how it came about, and how it has gotten out into the market. We'll talk at some detail about how the Hummingbird itself actually works and what is happening inside of the system to accomplish the damping. And then I'll wrap up with really a summary of what those key pieces of innovation are that ultimately brings us here today. So first of all, why is harmonic damping important? There we go. So according to the UN, 2009 was the first year that the urban population exceeded the rural population globally. And by 2050, it's expected that roughly 2/3 of the global population will actually live in cities. And to meet this demand, cities are increasing in density. One way that you increase in density in a city is to build taller and thinner buildings. But simply put, taller and thinner buildings are more prone to sway in the wind. Now, any structural engineer here can tell you this isn't principally a safety issue. These large buildings are actually designed to handle a fair bit of displacement. But it certainly is a human comfort issue. And the last thing that you want is for the person who just spent millions of dollars for your penthouse suite to not be able to live in it because of motion sickness. So the physics behind this, the motion behind these buildings' movement is extremely well understood. This is a well-studied phenomenon. And there are very reputable firms who specialize specifically in wind engineering and designing damping systems for tall buildings. If anybody wants to get into the weeds of specifically the physics on how these systems work, I'm going to recommend that you speak to our partner, RWDI, who is our wind engineering partner helping us bring Hummingbird to market. Let's talk a little bit about how or what the result is of all of this work. So you see the building on the left is an undamped building, and it may move quite a bit around a specific frequency in a wind event. On the right, you have a damped building where the motion of the damper itself actually clips the acceleration of the building around that particular frequency. And this is the fundamental intent of damping. As you can see, you end up with quite a bit less displacement or movement on the building that is damped. The ultimate attempt here, or the intent here ultimately, is to make it imperceptible to any of the building's occupants. So there are currently two main types of damping systems, passive damping systems, I should be very specific. On the left is a tuned mass damper, which is in effect a very large pendulum that sways counter to the motion of the building. On the right is a tuned sloshing damper. There are a number of types of tuned sloshing dampers, but this system uses the motion of water to actually accomplish the mass damping. The Hummingbird is an evolution of a tuned sloshing damper. Now let's talk a little bit about how it came about. So when NASA was developing the Ares rocket, they ran into a vibration problem. Specifically, launch vibrations that would kill the astronauts. Now, as you might imagine, this was not a desired design feature. So they also knew that the liquid that's inside of that oxygen tank would move out of phase with the vibrations of the rocket itself. And so they designed a damper to take advantage of that particular fact. But to test it, they didn't want to spend $50 million a pop launching a rocket. And so what they did is they put it on top of one of their very tall buildings. You can see that on the left there. That's actually the NASA test tower in Huntsville, Alabama. And yes, that is the Saturn V rocket inside of it. It turns out that the physics behind the motion of a building are similar enough for their purposes that they are able to get good data off the design and perfect the design, or at least advance the design for their needs on the rocket. So when NASA had pushed the design as far as they needed for their purposes, they looked out to the industry to see if there were any experts who could help them or who would be interested in taking the design and bringing it into the commercial markets. Thornton Tomasetti, who's obviously a very well-respected engineering firm with deep experience in the space, and particularly with very tall buildings, responded with interest and made a number of adaptations and improvements to the design so that it would work on an actual building. And this ultimately culminated in the installation of the Hummingbird system on a building in Brooklyn, New York. That the picture there that's on the left is, or on your right, I should say, is 461 Dean Street in Brooklyn, New York. I believe it's a building that's actually up for another award in this conference. It's tough to tell from that picture, but that particular day on the roof was about 20 degrees Fahrenheit, which is, what's -6 or 7 Celsius. And there was a whipping wind coming off of the East River. So it was pretty uncomfortable on the roof of that building, but I can tell you that the building was perfectly still. So this works. It's actually out in the field, and it's working on a commercial-sized building, not just a test tower with NASA. Thornton Tomasetti recognized that in order to bring it to market, they would better partner with a wind engineering firm, and so reached out to RWDI. And Thornton Tomasetti and RWDI have partnered to bring this innovation to market. Which brings us to today. As I mentioned earlier, Hummingbird is an evolution of the tuned sloshing damper, specifically the tuned liquid column damper. At its most simple configuration, the Hummingbird is a water column inside of a pipe with an air spring on one end. You can group these pipes together to create a damping array, and you can group these arrays together to create a large mass tuned damping system. This modularity has several significant benefits, and we'll talk about them. First, because it's not a single damper, it's actually a grouping of a number of smaller dampers. This system is extremely redundant and resilient. There is no single point of failure. If one of the dampers goes out, its impact on the overall system is effectively negligible. So that's a key benefit to the modularity of the system. Second, they can be made quite small. And the damper itself can actually be the single unit damper itself can actually be quite small. And what this means is, it is one of the first really practical solutions for damping existing buildings post-construction. It can actually be retrofit and fit into an existing building to help reduce motion post-built. Third, there's some interesting effects that you can get when you spread tune a system, meaning if you tune the damper around the native frequency of the building. In aggregate, the impact of that is to make the damper more efficient. For our purposes, it means smaller and less expensive. So let's describe at a really high level how the Hummingbird works. Inside each pipe, as I said, there's a column of water, and at one end, a sealed air chamber, shown here in orange. That air chamber is sized specifically to the frequency of the building. As the water column moves into and out of that chamber, this compression and decompression of the air chamber resists the motion of that water column. This is what is meant by an air spring. This action in aggregate is ultimately what dampens the motion of the building overall. A quick note, I'm sure many of you will notice that water does not like to maintain a perfectly vertical interface when set against air. So a large part of, or a part of the portfolio of patents on this particular product is how that water-air interface, that barrier, is maintained. So the air spring itself is a pretty significant innovation. Traditional sloshing dampers have very strictly controlled dimensions. And this is because the frequency of the building is what determines the length that that damper has to slosh. The air spring decouples that relationship. And so you can actually create, within reason, any length damper and still tune it to the frequencies of the building. What this means from a design standpoint is that you have an enormous amount of flexibility around how you would lay out and position the damper in a building. So you can see from these images here, these are variations of the same mass damper for the exact same building. On the left, you have a system that we designed by attaching it to the ceiling, hiding it in the ceiling of the building. This opens the entire floor plate up for other use. And in this scenario, you might want to use it for leasable or revenue-generating space. On the other side, you see where we vertically stack the damper. We're taking up some square footage on the ground, but we push it out into the walls. That maintains the maximum vertical space for any other equipment, for example, on a mechanical floor, that you may want to be able to fit in the save space there. These are just two examples, but you can fit this in and around any number of complex design constraints on a floor and still accomplish the damping effect that you want to accomplish. So let's summarize some of the key innovations here. All right, the first is this tunable air spring. At the end of the day, it just allows you to design the system in multiple lengths, which gives you an enormous amount of flexibility in layout. The second is this vertical air-water interface, which what you're capable of doing in that case is removing the upturned ends required of traditional tuned liquid column dampers. And that ultimately means that the Hummingbird is shorter and requires less vertical height to accomplish the same damping effect. The last, importantly, is this modularity of the system, which increases that redundancy and resiliency like we mentioned. It increases the efficiency through a spread tuning and really provides you a level of flexibility to fit the smaller dampers into and around other constraints, including as a retrofit option in buildings that are already built. So the big so what, right? What does this mean for a building owner? At the end of the day, it's more flexible. If there's anything that I've learned, design flexibility will make the architects happy, and if the architects are happy, everyone else is happy, right? It's more resilient, no single point of failure, and it's capable of handling anything that gets thrown at it. And then lastly, this is a lighter system. There aren't large concrete or steel tanks, and there aren't large point masses like there are with traditional mass or tuned mass dampers, right? So this is both lighter in aggregate and significantly lighter per unit area than other dampers that are out there. And what that fundamentally means to a building owner is that you need less structure to support the gravity load. And so that is Hummingbird Kinetics. Thank you very much for your time today. I very much appreciate it.